So looking at how we can apply determinants, if we have a system like this here, we can form a system of determinant ratios, much like in the 2 by 2 case, where we have x is dx over d, y is dy over d, and z is dz over d for non-zero determinant d. If you get a determinant 0, then you have a singular matrix of coefficients, and as a result, your matrix of coefficients is corresponding to a system that's either dependent or inconsistent, in which case can't solve it. But anyway, we're not going to worry too much about that here, because we have enough determinants to chase around for a little while. We have that D is the matrix of system coefficients. dx has the constants in its left row or left column, and then columns 2 and 3 correspond to the coefficients for the y's and z's. dy has the coefficients for x and z in columns 1 and 3, with the constants in column 2, and dz has columns 1 and 2 for the coefficients of x and y, and then the constants in z. And looking at this, yes, it is an ugly picture. For the 2 by 2 system, this was actually a slightly more efficient approach than elimination can be sometimes. But unless you get really lucky with determinants, the 3 by 3 case is basically never that efficient. And in general, I'm not going to ask you to do a whole lot with this in terms of a full computation. I may give you questions where this is a surprisingly useful approach, but I don't plan to ask you to specifically go through all of the steps of a 3 by 3 Cramer's rule problem just for the fact that it involves an obnoxious amount of work. So in our example and in the homework, we're going to focus more on being able to set things up.